Welcome to the another video of the electric drive. In this video, we will discuss the speed torque characteristics of the DC motor. Let us consider a DC shunt motor. If I draw the circuit diagram, usually the DC shunt motor is connected through a starter with a name nomenclature called LFA. And this starter helps to limit the starting current. Further, it is connected with the armature, and the field winding we can show it from the F point. Like this. So here the terminals may be named as, this one is F, double F, just like a starting and the finishing point. A, double A, the starting and finishing point of the motor or the armature, and the supply voltage may be given as capital V. So now you have a supply voltage, that is the line current which is going through it, IL. You have got a field current, some part of it will go to the field current, that is called IF, and the other part will go to the armature, that is called IA. The vital thing to remember is the IA and IF. And with the help of starter, which helps to limit the starting current, and further in the steady state, you have got a back EMF is developed over here. And this armature have a resistance of Ra. So this back EMF EB, we can write this EB is equal to phi Zn P by A divided by 60, where phi is a flux per pole. If the number of pole is 2, so per pole the flux is phi, even if it is 4. So accordingly, because the number of pole is mentioned over here, P, and A stands for the number of parallel path. We generally give the parallel path if the rating of the current rating of the motor we want to increase. So that if a wire carrying current carrying capacity is 5 ampere and we need to increase it to 20 ampere the motor rating, then we need to go for a 4 parallel path. Then P is the number of poles, phi is the flux per pole, Z is the number of conductor. Usually this Z is actually divided by the number of parallel path. And we formulate in such a way it is easy to remember. Phi Zn P by A divided by 60. N is the revolution per minute. So we can rewrite this entire expression as Z P by A, and this side we can write phi N by 60. So N is in revolution per minute. If I divide by 60, it is revolution per second. If I multiply here 2 pi and divide also by 2 pi, it will not make any difference. Now this can be written as, this entire thing constant we can write as KB. And here N by 60 into 2 pi, we can write this statement as omega M. And this will be multiplied with a phi flux per pole. Now the expression of EB can be written like this. Another expression that we can get it from here is the power which is developed in the armature is nothing but EB into IA. IA is the current which is flowing from the armature. So net power is EB into IA, and this power is converted into the speed and torque. So we can write this is equal to T mechanical torque, let us say shaft and other loss is neglected, so mechanical torque develop into omega m. So from this we can get the relation for Tm, that torque develop is equal to EBIA by omega m, where EB is equal to KB omega m phi into IA divided by omega m. So from here we can write Tm is equal to KB phi into IA. Thus we get the expression for the back EMF EB, and also we get the expression for the torque in terms of these flux, omega m and IA here. What else we can get it from this expression, this circuit diagram? Another thing is that what we get is, we can write V is equal to EB plus IARA. From this we can rewrite this as EB is equal to V minus IARA. And if I write this as, put the value of EB over here, KB omega m phi is equal to V minus IARA. From here we can write the expression of omega m is equal to, let us write down this, V by KB phi minus, let me just write IRA first, by KB phi into IA. Now IA can be replaced in terms of torque. So we can write here omega m is equal to V by KB phi minus RA by KB phi. IA is replaced as Tm by KB phi. Now this expression I am writing again here, omega m is equal to, let me write this expression first, minus of RA by KB phi whole square into torque Tm plus V by KB phi. So this is what the expression of speed with respect to the torque we are getting for the DC shunt motor. What else expressions we can get from here? We know that the voltage is fixed here. The flux, we can write also that the IF term is nothing but V by the resistance RF. Though we don't need this expression anymore, because if the voltage is fixed and the field resistance is RF is fixed, I don't need the value of this since the entire term is fixed. When it is important is the flux, which is field flux, which is linked with the armature, phi f is nothing but proportional to the current. So I can write that phi f is equal to kf into if. That is important here. Since the flux phi f is constant, we are not using this kf term in the entire expression. But if this flux will vary, if we need to vary the field current if, then we need to write down in terms of kf. But for now, this expression is enough. This one expression is enough. So let me take this copy of this circuit diagram and this expression in the next slide. So here we have taken that expression of these in the new slide. So another important expression that was left out is this that is EB is equal to KB, this one. So the back EMF EB is equal to KB times omega m times phi. Another one is the torque expression, Tm is equal to KB phi into Ia. Now this expression of these variables in most of the book may be written T, capital T, maybe T electromagnetic torque. So you need to understand that the torque which is developed over here by the motor is the electromagnetic torque, and when it is this torque is transferred from through the shaft to the load, then it is the mechanical torque. So the electromagnetic torque is obviously more than the mechanical torque, but if you neglect it, then all these terms are okay. So these are some of the expression that is used to draw the speed torque characteristics of DC motor. So what exactly the speed torque characteristics we are going to draw is, on the y-axis we will be keeping our speed, and the x-axis will be drawing the torque. So let us take this expression first, and this is the most important expression. So if I take the value of Ra, let us say 1 ohm, armature resistance is 1 ohm, and I take the value of phi as, let us say, 0.8 Weber. Let us say the applied voltage is 220 volts. Then you have KB. The KB we can get it by these constants, or for, let us say, for a moment when the loss is not there, EB maximum value is V. So we can evaluate the value of KB from there, or we can get, because the KB is nothing but a constant term. These are the Z into P by A divided by 2 pi. So these terms are constant, so we get some value of the KB here. So what exactly this term is? This term is nothing but y is equal to minus of x, minus of slope is minus of m, slope is m, x plus c. This is the expression that we can see on this side, where y is nothing but omega m, that is what we have in the y-axis. X is the torque minus m. M is the negative slope. Because of minus sign it is negative slope, and the value of m is Ra in the numerator, and denominator is KB phi whole square. So like this, denominator is very high value, so the slope is very low, and another is the C. C is the V by KB phi. So obviously this value is V on the top is like a very high value, so obviously we'll get the starting point over here, and this will be called as omega m0, or the intersection point in the y-axis, omega m0, which is nothing but V by KB phi. And if this slope would not have been there, then this would have been a straight line. Y-axis is equal to C. Because of this negative slope, we will get a curve like this. So that is the expression of this equation, what we see. This is the curve for this mathematical expression. Let the motor is driving a load, and the load torque is given by TL. Load torque is given by TL. Then the intersection point is the speed at which the motor will rotate, or this is the stable region or stable point at which the motor will rotate. So we here discuss not this, what is a stable point, rather we discuss that for a fixed load TL, or for let us say it is running a rated load, and the motor is running at some speed omega r or omega mr at this speed. Now what happened in this speed torque characteristics, let the question arises, number 1, if the armature resistance is changed. So one cannot change the armature resistance. It is common sense because the armature winding is there. So what we can do is, change means we can add extra resistance over here. You cannot delete any resistance, rather you can add extra resistance. So now RA will be changed to RA plus R external. So this is one, we can add a resistance. Similarly, second thing is that if the supply voltage is there, can you change the supply voltage? The point is, you cannot increase the supply voltage because everything is governed by some insulation. There is no chance that you can increase the supply voltage. Yes, there is a chance that you can decrease the supply voltage. So this supply voltage you can decrease to some other value. Third options, what is that? This current which is going through the field winding. So because of this current IF, there is a flux which is linked with the armature. Now this IF, can you increase? Because you cannot increase the V, and V is not to be disturbed, V is fixed. So is there any chance that you can increase the value of IF? I think there is no chance. What is possible is that you can have a diverter over here. You can connect a resistance which will act as a diverter, and the current which is going through the field winding can be decreased. The current which is going through the field winding, that can be decreased. If that is decreased, what exactly you are doing? You are decreasing the value of the phi f. So phi f is actually you are decreasing. There are three possibilities over here. One is a armature resistance change, one is a voltage change, one is a field current change. So if field current is decreased, the flux phi f decreases. If flux phi f decreases, it leads to some effects. So the first one is called armature control. So there is a speed control using armature control. Then another is voltage control, and the third one is flux control. So there are three methods to control the speed to control the speed of the DC motor. One is armature control, voltage control, and flux control. Now if the value of R is external, if we add external resistance, what does it affect on this equation? If we add external resistance over here, by writing it like this, the slope is going to increase. By adding an external resistance, I am actually increasing the slope. And there is no effect in the value of the C. Only the thing is that the slope is increased. So if the slope is increased, what will happen over here? We can see that this is the MATLAB simulation output with having different armature external resistance. Here it is. So here let us say this value is omega m0, and here is the value of R0. Then the external resistance, this R0 is only, you have RA, armature resistance is there. Now you have external resistance R1, then you add external resistance R2, then total resistance become R2, then total resistance become R3. Obviously this R3, R1, this all are greater, all these values are greater values. So moment you have the values of R1, R2, R3 and R4 greater values, it changes the slope, because slope is equal to armature resistance plus external resistance divided by KB phi whole square. And thus you have got Y is equal to minus of mx, x is this side torque, plus C. The C is going to be the constant term, so you have this fixed value. So if you have a load torque like this, if you have a load torque some value, So if you increase the armature resistance, your speed will be decreasing in this way. If you have a very heavy load, if you have a very heavy load and if you increase the armature resistance, the speed will also decrease a little bit in a more high ratio. So it depends on what is the load torque that decides your how it is going to decrease. Now let us take another value that is the voltage. So what we can do with the voltage, you can only decrease the voltage. So voltage can only be decreased. If the voltage is decreased, so which parameter is going to change? That only the parameter which is going to change is the constant value. The slope is not going to change. The slope, if RSE is out, the slope is not going to vary anymore. If the voltage is decreased, so the value of the constant is decreased. So you will have a slope which is going down. Same slope, but the intersection point omega m0 will obviously going to change. We can see this in the one MATLAB simulation of it, where the voltage is varied. So here you have the alter voltage V is equal to 220 volts. Now the voltage is varied to 200 volts. Then again 20 volt is decreased. It is now 180 volts. Like that the voltage is varied. So there is only thing is that this by using the armature resistance, suppose there is a load torque and you are decreasing the voltage, this is how the speed is going to vary if you decrease the voltage. So y is equal to minus mx plus c, you are actually decreasing the value of c here, not the slope m. Let's see the equation of this is omega m is equal to minus Ra by Kb phi whole square, this much into T plus V by Kb phi. That's the expression for that. Now one thing we have neglected over here is that if the supply voltage decreases in the DC motor, the current IF will also be going to decrease V by RF. If the supply voltage decreases, this will decrease the value of the IF. And now if IF decreases, this will lead to decrease in the flux phi F. So if the flux decreases here and here, the slope might this will get increased. And here also it will try to affect. So if the motor is separately excited DC motor, so if a motor is having armature over here and you have a field winding connected separately where is IF and this voltage is V, then you can have the option of decreasing the value or not decreasing, this field supply to the field winding remains constant and supply to the armature, this value will decrease and then you will get this type of effect. In DC shunt motor, if the supply voltage is decreased, you will not get this type of waveforms. There it have a multiple effect because of decrease in the voltage, there is a decrease in the flux. So this must be remembered that this spatial speed torque characteristics will be there only for a DC separately excited motor. The third option that is available over here is the flux. That is only you will change the flux. The voltage and the armature resistance remain constant. Only the flux need to be varied and the only option is that you can decrease the flux. So if the flux is decreased, what is going to affect? If the flux is decreased over here, 1 and this one, though this will affect the value of the C, C will increase definitely, but the slope will also be increased to a higher value. So we try to get the curve for this particular thing, that if the flux is decreased, how does it affect this line? And what we get, let us see. You can see that this is the output, the simulation output of that, and this is what is you have at no load. This is one it is to have with no load, the first one. The axis has been changed. Earlier the axis is from 0 to 200, now we have taken the y-axis 0 to 3 and 500. This is in radian per second. I can show you from here. Earlier we are going from 0 to 200, now it is from 0 to 500. So now when the flux value at this particular, the flux value is 0.8 Weber, now it is decreased to 0.6. Now here it is 0.4, here it is like 0.7, sorry, 7, this one is 0.5, 0.4, 0.3, 0.2, and like that we try to decrease the flux value, and what we get is this is going to, at 0.1 it is going somewhere, we are not able to get the range also. However, the flux is decreased, we cannot go on decreasing and expecting the speed to be like very double, triple times, because this is in radian per second, so here the speed is nearly 1500 RPM, revolution per minute. So when we are exceeding the speed, so obviously the torque will decrease so as to keep the power constant. But here the power value is equal to EB into IA, and that is equal to T into omega m. So this is the expression. Now if we try to draw more and more power from the source to keep the torque constant, it may happen that the wire will get burned, it will draw large amount of current. So we cannot go on exceed the speed. We need to keep a check that the power has not exceeded the limit, because in this particular case, since the current is, this is separate, let us say it is separately excited DC motor. In a separately excited DC, because all these things are like for an ideal case where a separately excited DC motor is there and you have got a field winding separately connected. So here armature current is now controlled with a supply voltage with having an EB over here, and what you are doing is you are decreasing the value of the field current and you are expecting the speed to increase. So if you go on increase, that will IA is remain same, so it will lead to some EB value. The EB is actually equals to KB phi into N. So if this phi you are decreasing the value of the phi and you are increasing the value of the N. So in this way you are trying to keep the EB constant. But again, if this EB value and IA value is together, multiplying by these two will lead to the constant power. Thus, we can also write this same expression as KB phi. This is not N, this should be omega m. So anyway, if the value of omega you are increasing by decreasing the flux, if the value of the omega is increased, so we are trying to keep the EB constant. And if the load torque is increased anyway, if the torque is going to increase, that will lead to increase in power. That means the more and more current will be drawn from the source, and this may affect the winding, armature winding, and lead to hazards. So therefore the rating of the motor must be kept in mind while doing for the increase of the speed and also up to what value we can increase the speed, that also need to be checked. Otherwise it may attain a high centrifugal force. So this is what we have discussed on the speed torque characteristics of a DC shunt motor. In another video we will be having a discussion on speed torque characteristics of DC shunt motor, DC series motor, and we will also see how we are getting the speed torque curve from that. So thank you very much.